let's get this started. So it is my pleasure to introduce our speaker today, Professor Buseck. It's kind of a long introduction, so bear with me. So he's been around for a while, as you can tell by the title. He's been in this field for 60 years. Columbia in 1962. Went on to the geophysical lab and did experiments there and came to ASU in 1963. He's made huge contributions in mineralogy, meteoritics, geochemistry, and atmospheric chemistry. And a lot of this has to do with the subject of what he's talking about, and that is electron microscopy. So he was here in the early days when Leroy Eyring was helping to set up the Center for Solid State Science and the Center for High Resolution Microscopy. Under John Cowley, and Cowley brought in a postdoc named Jima, but the beginning of local crystals with high resolution microscopy, seeing the details of the structure. Now, before that, most of what we knew about crystals was where all the atoms are supposed to be, right? So when I talk about crystal structures, I talk about atom positions, where the atoms go. But what these microscopes allowed us to do is look at defects. So Peter was there, and of course, put minerals in the microscopes. And minerals happen to be great things to look at because they're full of all kinds of defects. And so Peter is very much known for this huge contribution to mineralogy in the high resolution imaging minerals, defects to processes, geologic processes, and planetary processes, and so on. He also studied meteorites, and there are several meteorites here. So Lawrence Garvey's here, he studies meteorites. And he's mentored many people who've studied meteorites over the years. But I just want to tell one story. Before Tomioka and Buseck, the fine-grained stuff carbonaceous compound was called CP, poorly characterized phase. It's not called that anymore. The reason is because of electron microscopy and Kazu Tomioka and Peter Buseck. I mean, so he was involved in lots of really important milestones in the mineralogy of meteorites and terrestrial rocks. But it's not just that. At the same time, he decided to start looking at aerosol particles. So aerosol particles, these things floating around in the air, have been studied in many ways, but not in detail with microscopy. So with his postdocs and students, they worked out how to study thousands of particles by automating the SEM to look at these things and figure out what they are, what their properties are, and apply those to their physical properties. And these are huge contributions. So, yeah. But Tom, what was he like as an advisor? So, as many of you may not know, he was my advisor. So now the dirt comes out. So, what he provided for his students and postdocs, he provided the infrastructure, the resources, and the community for success. And all those things are really important. He also provided the freedom for us to kind of do whatever we wanted, but the freedom to act or to succeed, and always a nudge to do something new, to keep pushing the edge. So that's how his work was. As a student, I didn't fully appreciate it. And I told you that once before, and he didn't like hearing that, but that's because as a student, I was stupid. When I look back now at how his group has worked over the years and all the people he has mentored, and what he's done in the community, I think it's fantastic. It's true, and I'm proud to introduce Peter Buseck, our local speaker.
Thank you, Tom. Thank you very much for the nice introduction. I need to tell you something. It is true that I started here in 1963. But Tom didn't tell you I was 12 years old at the time. All right, so let's see what we can do. So this all started, well, no, I was here for a while as an economic geologist, really didn't like that. And then in the 60s, I became interested in electron microscopy. we recruited John Cowley. Some of you will know his name from the Cowley Center. This is, see, there's also a pointer here. That's John Cowley. And we recruited him in about 1970. And with him came a young postdoc, Sumio Ujima. And Sumio, at some point, I realized great to work on minerals because all the work until that point was on oxides and things of that sort. So I had some money for a postdoc. So I asked him to join my group, which he did. So he's now world famous scientist. All sorts of work. At that time, he was just starting out. And then to write the paper, I had a bad skiing accident. So he came over and we went to the paper in my backyard. This is not me. I had a broken collarbone and ribs, but I couldn't find a picture, so I thought I'd take this one. So the result of that was the first comprehensive study of nanomineralogy. And although the word hadn't been coined, we didn't even think of it at the time. So it's really difficult to have to look up here. So what I'm going to do today is just tell you several stories of things that we did over time. The topic is over a half century. So a few stories. First, and it said, one has to love them. Pyrite, rhodochrosite, and beryl, we'll see that some more of it. Here are a bunch of gems. We don't need to go through them, but you can pick any color you like and you'll find a beautiful gemstone. And these are diamonds, which are mostly not so interesting, but once in a while, they're nice ones. Well, there. So this a friend of mine, the curator of the whole diamond is a former PhD student of mine. He's been at the museum for a long time. It's probably the sweetest job in mineralogy in the country, the world. Anyway, so here's what I'm going to do. I'm going to talk a little bit about transmission microscopy and why it matters. We're talking about crystal irregularities. And then we're going to do a little bit of talking about extraterrestrial planetary minerals, mainly from carbonaceous chondrites. We've done other things, but not time for that. We'll do a little bit on life on Mars, and then the most current work on new carbon species and interstellar medium. So we published some material on this, but much of this is not published. We'll see this slide again. Anyway, let's start out. It's okay. So should I start over? All right. Diamond is generally considered the most valuable mineral. This is next. This is an emerald. And the peculiar thing about it, and it's a wonderful mineral, but it's full of holes. Just chock full of holes, which is really surprising. This was the first mineral we decided to look at. And here's a picture of it. Here you can see all, and this is 9 angstroms. I'll show you what 9 angstroms is, but note the tunnels. And this is the first time something like this was seen. And to try to give you an idea what was involved, you have these long tunnels in a crystal, but if you don't look exactly down them, you don't see anything. So a lot of effort is spent tilting the crystal. And analogy, I thought it is straws, and you can imagine just a handful If you want to see me or vice versa, I have to hold it just right. So that's part of what's involved here. But what about magnification? What does that mean? So um, the Burrell channels are about 1 nanometers or 10 angstroms. It's hard to understand that if you're not familiar with it. If you're fine, if you're comfortable with a billionth of a meter, you're good. But I thought, let's see if I can come up with some analogy. One is the diameter of a human hair, and another is the story of the battleship and the seagull. So let's do that. Here's the human hair. And again, Hope Diamond on my buddy here. And this picture, I like to kid my son that he had a big hairdo. That's this kid him that's isn't. But here's the hair. Here's the hair of Earth. And each hair, one of yours, you can pull one out. You can put 100,000 nanometers across the edge of that hair. So a nanometer is pretty small. Here's another measure, the battleship. Now, supposing a seagull comes along and lands on it, it will sink it by 1 nanometer. And if its baby comes along, that'll go to 1/10 of a nanometer or an angstrom. So that's to give you an idea. Of course, the battleship has to be in a calm sea for you to notice a nanometer sinking. But that's the sort of thing we're talking about. So it's quite extraordinary. This is a nanometer on our barrel crystal. So this at the time caused a lot of excitement. People didn't know this could be. And all of a sudden, it was possible to do things on an unprecedented scale. Now, I need to tell you that they were revolutionary, but I want to tell you that they're not just curiosities. For example, there's a mineral called zeolite. If you've had mineralogy, you would have encountered it. It's an aluminosilicate, and the microcavities in zeolite is used for all sorts of refining, and it's a multi-billion-dollar industry. I'm not going to talk about it, but it's because of those microcavities. The same thing. Well, I'm going to talk about defects in a moment, but they're critical for computer chips, batteries, fuel cells, all sorts of things. But let's get back to mineralogy. So here's the issue. One of the issues. You've studied metamorphic rocks, and you know you go from one type of metamorphic rock to another. But how does that happen? How can you? And they're solid. How can you get one mineral changing to a mineral in the solid state, especially if there's slight differences in composition, as often there are? And the other thing I'll talk here is a little bit about asbestos fibers and see if all asbestos fibers are equal, which they're not. So here's a picture of amphibole, and this guy worrying about it because there's a big hole. We're looking down, for those of you who had mineralogy, we're looking down the length of the amphibole crystal. So, the important thing with electron microscopy is see defects. And this is an example of a defect, this hole. Those of you who studied amphiboles, you may know I-beams, and we have a missing I-beam here. The interesting thing is it's very large. See, it's 27 angstroms. Most atoms are just a few angstroms. So you can just have a lot of material going through there. Even have water going through. All of a sudden you can have a non-solid material. You would know by another technique that it has really need high resolution microscopy. By the way, Tom is an expert in microscopy, and so is Lawrence Garvey, who's out there somewhere. So if you need advice, and so is Rhonda. There's a bunch of microscopists here. So they can confirm what I'm telling you is true. So here we have this big hole. If we turn this sideways, then we get this very peculiar thing where we have regions which normally we would call this one mineral, This would be another. This is a width of 3 I-beams here, 4. This is a highly disordered crystal. Again, you wouldn't tell that from the mineralogy lab or even with a microscope. There's a lot going on here. So this is really a case of metamorphism caught in the act, because that'll be okay. Okay. One of those phases with light beams is going to nano beams is going to metamorph larger and larger. There's a family of these are new minerals. I had a postdoc long ago named David Veblen, and there's his name. And he and we studied these, and it was a very interesting study. This is a picture of these 3 minerals. You can see they're color coded. Okay, let's go on. Told you we're going to do this quickly. Let's talk about asbestos. You can see these sorts of faults or mistakes in the structure. We call them zippers because obviously because of the way they look. But here's the interesting thing: is there's bad asbestos and there's harmless asbestos, benign asbestos. So it's bad versus benign, amphibole versus serpentine. The EPA requirements and all the issues with being protective of asbestos is very, very confusing. Much of the asbestos, and asbestos just means fibers, much of it is this stuff. Amphibole asbestos is like this. This is amphibole. There's a question of how fibers formed, and I think that they're formed by these defects. And I think that its defects are also what are chemically reactive and are the cause of cancer. Mesothelioma is a form of cancer. Famous geologist, fellow alumnus of mine, Steve Gould, died of mesothelioma. Very sad story. So let's do one more slide about asbestos. Here's some fibers. Here's fibers really coarse. Here's with electron microscope, optical microscope. This is rebekite. There are all sorts of varieties. We needn't worry about that. And here's an interesting picture. This was taken by a postdoc long ago named Jung-Ho An. And you see there's this piece here fits in with this. You'll see in the next slide, these arrows show the crystallographic axes, and they're a little grain boundaries, and each of these are at a slight angle. So these are regions also where one can get alteration. If we blow these up, it's like this. And these call them zippers. I think here I just call them crystal defects. I think this is what accounts for why some asbestos is dangerous. The other kind is called serpentine asbestos, and there are 3 types. This is the 3-headed dog guarding the gates of hell, if that's something you're into. The 3 types is flat or lizardite. You can see the structure. So this is faded, the pointer. So I'll just, if there's another pointer, that would be good. But so there's the flat type, wavy type, and the bottom type is tubular. That's the fibers, and that's the benign asbestos. I'll show, and here, quite nice. Here are the cylinders. I'll show you some pictures of those. There's one cylinder, and you can see all the layers. And an interesting question is, what's going on in the center? And it's so fine-grained, we've not been able to image it. So this is looking down a fiber axis. Here, they also occur in meteorites. Here's a nice fiber. And this is from a carbonaceous chondrite. Here is fibers looking sideways. Tom Sega, a PhD student, he's now a professor at the U of A. He was a postdoc with Rada, so there's a lot of connections. But this is another type, nice meteorite. Are you looking for a pointer? So now we've had enough of that. Let's talk about Mars. Long time ago, I don't know how this works. Oh, there we go. In the 90s, I was at an international congress when all of a sudden through the halls, have you heard, have you heard, have you heard? And it was President Clinton who announced, President talked about geology and mineralogy. He said there's evidence for life on Mars. Just as an aside, there was another time I was at an international meeting, this time was in Rome, and there was a lot of buzz through the hall. Have you heard? Have you heard? And that's when the planes struck the towers in New York. So I don't know what the significance of that is, but exciting international conference. We hear about life on Mars. Well, the story, there it is. So here's my story. The evidence for the life were crystals, tiny crystals of magnetite. That's almost correct. That should be iron, Fe3O4, in a Martian meteorite. It's a magnetic. And it was proposed that their unique shapes could only come from magnetotactic bacteria. Those I'd never heard of them, but I'm going to show you what they are. They're very interesting things. So I thought this is really something worth pursuing. At the time, I had a fairly large group. We talked about it, our regular group meeting, and we thought we maybe should check the results. So I'm going to show you now what we did. We got some crystals of this sort, supposedly from Mars. In principle, here we go. So this little magnetite crystals, it's a whole necklace or chain of magnetite crystals, and they're within a bacterium. This is really weird. It turns out that you can go almost anywhere. And if you take some mud, take it home, take a magnet, you'll get some stuff attracted by the magnet. We collected this sort of thing in countries across the globe, in Hungary and Brazil, here in the country. Why do bacteria have magnets? It's a really interesting, maybe you know. What they do is they use them to find food. Now, how do they use magnets to find food? Turns out they align themselves with the Earth's magnetic field. So they're in water and they don't know, their eyesight isn't good, so they don't know whether to swim up or down, but they can align themselves with the Earth's magnetic field and swim down to the bottom and have their feast. So I'll show you some more pictures because this is a really interesting sort of thing. This is called a holographic, which doesn't matter what it. These are each individual magnetite crystals. This is a chain, and these are magnetic field lines. So it shows that they're not only are they individual crystals, but they're all oriented the same way, which is cool. This is a prettier picture. Some bacteria have their chains in pairs. We don't know why that's why it's single pairs. Here they are. This is again holographic image, and they're quite beautiful. And again, by the end of the talk, I'm going to know how to do this. These are the individual crystals, and you see these magnetic field lines are right here. So the magnetic field is perfectly aligned there, and which is perfect for gobbling food. Here's another picture of bacterium. And here are the crystals. Now, the big question is, what are their shapes? The whole argument, this was a whole group led by some people from NASA about life on Mars. They found these little crystals, said they must come from magnetotactic bacteria, which means there were bacteria on Mars, life on Mars. Big deal. They made a big point of their shapes. So here are the shapes that they proposed, all of these. It's two different groups. Here's what we did. This is part of a bacterium, and here's the chain. And what we did through tomography, we were able to get these crystals different angles. And so nice, we'll do that again. No, we won't. The big deal is the shapes that we found don't match those that these teams that reported life on Mars did. This caused a big hubbub, and it went on for some years because the group that reported life on Mars really were strongly invested. You'll find out in science, you get a great idea. It's hard to like, that's easy to understand, but it led to quite a long discussion. But here's our conclusions. Magnetite crystals indeed occur. Their sizes are similar to those in magnetotactic bacteria, but their shapes don't match. So we concluded that the Martian crystals are not bacterial in origin, and they don't provide evidence for life on Mars. That is now widely accepted. It took a long time. Not that there's no life on Mars, but not good, convincing evidence. However, the good thing about it is this was such a big deal. Again, the president announcing it, it was the stimulus for forming the whole new branch of astrobiology and NASA, which funds a lot of people at ASU and across the world. So that was good news. And the other good news is there's still room for additional work. So now I want to talk about carbon. 29, I didn't know this. We've been working on carbon. Time, but I learned that team was the year of carbon, 100 years. So we're going to talk a little bit about carbon. There are two major forms of carbon. One is diamond, where the bonding is three-dimensional. Each carbon has four neighbors, and the other is graphite, which is layered. The big issue, and I'll show you this in another slide, is what about one-dimensional carbon? This is three-dimensional, two-dimensional. What about one-dimensional? So first I need my graphs. If you use graphite, it's my late wife. This is a nice diamond, not hers, not ours, but at the time it was worth $26 million. Now it's probably worth a little bit more. By the way, if you ever visit Jeff Post at the National Museum and you're very nice to him and you tell him you're from ASU, he'll show you even much bigger diamonds. They're locked up in the back. So I just thought I'd add this here. It may be indistinguishable from a diamond chemically, Harry, but to me, charcoal is charcoal. So there is a difference between diamond and charcoal. She seems to prefer a diamond. Here's a picture of a nano diamond in the Murchison meteorite. Lawrence Gardy in the audience has done a lot of work on nano diamonds. This is an interesting picture where this is graphite. The layering of graphite is evident, and this is the structure of diamond. And this paper was about conversion of graphite to diamond, diamond to graphite. Here we see a very rare intergrowth. In general, diamond is a high pressure phase, graphite's low pressure, so we don't find them together so often. A long time ago, before that work, I thought it'd be interesting to look at poorly crystalline graphite or carbon. I thought maybe this is a way to find Precambrian life. It was one of many great ideas that didn't pan out. We looked. So here is very poorly organized carbon. No evidence of life that we can show. Metamorphic rock gets more and more crystalline. So here it's quite graphitic. This is synthetic. It's annealed. So we went from cold to hot. All show some graphitic layering. They show some disorder. They show some defects, but there's no evidence of early life. So we didn't find it in Mars. We didn't find it in Precambrian rocks on Earth. But we did think it's worth pursuing something else. So here's a diamond, three-dimensional bonding. It's called sp3 bonding diamond. sp2 bonding is graphite or fullerene or buckyballs or nanotubes, all of them. And I'll show you that again in the next slide. And this is something new. We decided to see if we could do something with pseudocarbine, or we call it pseudocarbine, about sp carbon. I'll tell you that in a moment. This picture of diamond, 4 single bonds to each carbon atom. It's the hardest mineral known. Graphite, we have 3 bonds to each carbon. It's the softest mineral known. And that's because these layers are each strong individually, but they slide over each other. So there's 1 pi bond associated with each atom, and that gives for great strength within the layers, but not between. Fullerenes were discovered in 1956. Shortly thereafter, I'm sorry, I had that wrong. 1996, there was a Nobel Prize for this form of carbon. 10 years later, there was another Nobel Prize for graphene. Again, sp2 carbon. So that's, and the reason is not just because it's strange bonding or surprising bonding, but carbon is one of the most important elements. It's one of the most versatile elements and valuable properties to it. Geologically, industrially, big deal. So sp3, sp2, what about sp carbon? That would be linear chains. So solid, but however, solids consisting of chains are not known. There are a lot of reports in the literature, but they're not known. But there's a lot of interest. Again, Nobel Prize for fullerenes, Nobel Prize for graphene, for probably Nobel Prizes for sp carbon. The material is called carbine, and that's a name of a solid consisting of infinite chains, but it's unstable. I'll show you that in the next slide. The chains cross-link. This is a group of people. We got together to study this. Actually, the story is somewhat interesting. We did work many years ago on fullerene and other forms of carbon, and I received a call from one of the co-founders of Walls, had a Nobel Prize. When he shared the Nobel Prize, he asked me to look at a paper, see what I think someone reporting sp carbon. And I looked at it and I told him what I thought, but it appeared anyway in a different journal. So we thought we better check it. It seemed quite strange to me. So we put together this team to explore it. Here's what happens. There's a single chain of carbon, and what happens is they cross-link, and they do this explosively. So solids of single chain carbon, even though people report it all the time, they don't work. At one point, I had the slide saying boom, 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 but I thought this is enough to show it's an explosive mixture. So, however, we came up with the idea that maybe carbon chains could be stabilized if we put small clusters of atoms in them. And we came up with a name calling, instead of carbine, call them pseudocarbine chains, carbon. Here's another chain. This is Harry Kroto, is the Nobel Prize winner. This was his last paper, by the way. So these are carbon chain vibrations in the along the chain, and these are the metal clusters that we hypothesized occur there. We're still working on. Here's a TEM image. This was taken by Jun Wu, who's here now. He was a PhD student of David Veblen, who I told you something earlier on, so he's sort of a grandchild. Here's a picture which is blown up here, and the question is, we haven't confirmed that, is whether this might be showing what we hypothesized as the structure of pseudocarbine. An interesting thing is when we synthesize this stuff, it starts out looking like this. You see some fringes, but nothing distinctive. With time, we develop these folds. So all these dark spots are gold. So it seems that that comes from this material. So there is, and we synthesized it with gold. So that, but not as part of the material. I tell you how we do it. Put a sheet of gold into an organic solution above it, and then with a laser beam, we pump a lot of energy into that, and it connects with the gold. It breaks apart the solid to give supposedly the. But we think that it comes as well. Here's the material from don't see gold. Find here to vary. So let me tell you a little bit more about pseudocarbine. Its infrared spectrum is indistinguishable from compounds called polyions, which are chains of carbon with hydrogen at the end. Note, they're not solids. They don't form in solids, but they do form in molecules in the gas. If you take a spectrum of them, the spectrum of those, when you calculate them, are the same as the spectrum of pseudocarbine. So we hypothesized that we looked at a spectrum, observation IR spectrum of this carbon star, and it has all of these peaks, and this region here is a region of iron pseudocarbines. I don't know if you don't have to worry about what these are, but this is the synthetic spectrum. This is the observational spectrum. Pretty good match, and there's a plausible case for iron pseudocarbines in the interstellar medium. Again, this is an image of a star, so it's through the interstellar medium. We submitted a paper to the Astrophysical Journal proposing this, and we told them why we think it happens and why it's important. One of the reasons we thought, I didn't put in the slides, I didn't think I'd speak those quickly, but if you look at a map of the band in the center of high density, and you have magnetic lines through that, the general thought is this is due to iron clusters, but could be that it also could be through iron pseudocarbides. The intensities are pretty comparable. Another thing that, so I have to tell you, a very interesting feature that if you look at the molecules that you from the interstellar medium reported. Most of them haven't been identified, but the ones that have been are either small molecules or large molecules. There's a gap in between, very peculiar. Little ones, big ones, nothing in between. We propose that iron pseudocarbines are catalytic, and they are what explain this compositional gap. Anyway, it was plausible enough that the physicists, we pulled them, we took it and published it. So I'm going to sum up now with transmission electron microscopy. We looked at insights into crystal irregularities. First, we looked at regular ones, then their irregularities, and why they were useful for tracking and understanding mineral reactions, for example, metamorphic reactions. Then we looked at meteorites. We did look at interplanetary dust particles. I didn't put it in here, but we also found very interesting things with them. But anyway, we looked at fine-grained minerals, and I think Tom said, not sure. When I grew up geologically or mineralogically, the stuff in carbonaceous chondrite was just stuff. We didn't know the mineralogy of it. So I thought maybe we should take a look at that, and we did. I had several excellent students and postdocs who did work on that. And then I told you about life on Mars. Let me just tell you a little bit about the stuff on carbonaceous chondrites. Some of you may know manganese oxide that has the elegant name of WAD, W-A-D. It was not known what that is. And so again, we were on the crest of a wave. We were able to do microscopy. Lots of students and postdocs. So several students look at WAD, and we found there's a whole series of manganese minerals there, and that they have some interest geologically, also for batteries. So, and that is because combined together fine-grained minerals. Then the interstellar medium, we speculate the carbon-rich species. We also think that these may well be possible in the lab, in which case they would be very useful. Their spectra indicate that they may occur in the interstellar medium, and this is ongoing work. So some of the things I showed you has not been published yet. Since I have time, I didn't know whether I would. I stuck in a couple of interesting slides. A mineral called chlorite. This is a different sort of mineral. It's a simple mineral called lizardite and asbestos. And this would be, if you just looked at that, it would be chrysotile. Well, what's going on there? We have no idea. This made it to the cover of Science magazine. They colored it green because it's serpentine, but originally it's black. But we don't know. Here's another really interesting picture. You see here, chrysotile. This is curved. This is layered. This is layered, but wider layers. So the minerals, okay, there we go. In yellow is asbestos, a single fiber. Here's one, but still chrysotile. Here is layered serpentine, lizardite, and here's chlorite. Remember, I told you the Cerebrus, the dog guarding the gates of hell. These are two of the serpentines. Strangest picture. Have no idea what's going on. This is serpentine. We've blown up. This fiber over here, this there, this here. Don't know. They have holes in the center. What's in the holes? Don't know. I like to say vacuum, but that doesn't make any sense. But we don't see anything in them. So that's the end. and we do electron microscopy. Thank you very much.
All right, we have time for questions. I know there are some students out there, in fact, some mineralogy students. I really want to have some students ask a few questions if you've got them. And remember, you can ask him anything
Anything at all.
right here.
You may have to tell me what the question is, Tom.
Okay.
So in however long, okay, there's the carbon, the interstellar medium, whatever, the you work that out. Then what? If we see the carbonites in wherever we're looking out, and I think you said in a star from that spectrum, what does that mean for
Tom, can you tell me what the question is?
Why are the interstellar pseudocarbines important?
Why are they out? So the simple answer is we don't know. On the other hand, we don't know why any of the molecules are in the interstellar medium. There's some 100 molecules have been identified. The astronomers, what they like to look at stars, and they like to look at the gas between stars, and they identify all these different molecules. There are also many things that have not been identified. But the interesting thing is that the spectra of the pseudocarbine is the same as molecules that they have identified. But all of a sudden, we have a molecule that contains iron, plausibly, we're not sure, because the spectra are identical. If it contains, then we can explain some of the things that we're having trouble with, like the magnetic field. Is that responsive?
Yes, thank you.
Okay.
Other questions? Well, we've got some back there.
Is it possible to see zoning within a magnetic crystal, magnetic and non-magnetic regions?
I'll repeat the question. Is it possible to see zones in magnetic crystals with magnetic and non-magnetic domains?
Is it possible to see what?
Non-magnetic and magnetic domains in a, say, a magnetite or magnetic crystal.
So is it possible to see magnetic versus non-magnetic zones or regions in a magnetic mineral? Absolutely. Absolutely. First thing is this down. So there are conditions we might think of. There could be, just as I showed you, integrals of what we might call, if they were macro, two different minerals, but they're intergrown on this nanoscale. If one is magnetic and the other is not, we can tell that. The other thing is if we do holography where we look at the magnetic field lines, we again would see the field lines bent where it's not magnetic. So the answer is yes, and that would be an interesting problem.
And for example, some of the use of that holography image to look at magnetic domains in materials using the same technique.
Right.
Other questions? We've got the microphone is there anyway.
Do we have any theories about how magnetite crystals form on Mars, since we know that it's not from bacteria?
I'll repeat the question.
Please.
How do you think magnetite crystals form on Mars, if not from bacteria?
How did they form on Mars? They formed the same way any other mineral formed on Mars. So the question is, how did minerals form on Mars? That's beyond my pay grade and certainly beyond the time we have now. But long and short of it is, I don't know, but not from bacteria.
Thank you.
Which is a shame. It was a nice story.
Other questions? So let's get the one back there since we're back there, and then we'll get you next, Larry. Yeah.
Hi, thank you for your talk. This is more of a general question, but having been in a particular field for so long, is there any, like, would you have expected the field to evolve that way or in the directions it did, like when you started?
Do you expect the field to evolve the way it did?
Did I expect it to move the way it did? Impossible to expect that. Impossible. I thought it would be very interesting to look at minerals the way that the physicists were just starting to look at titanium oxide. They found a set of what are called homologous phases in the titanium oxides. Physicists were doing that. I thought it'd be fun to look at minerals. I had this idea because I always was interested in minerals, and because I was really being turned off by what I was doing in economic geology. I didn't like that at all. So, and I loved minerals, so I thought that would be fun. No idea. What I didn't anticipate, what we found in the first initial paper was the defects. And once we found defects, then all of a sudden that opens up a whole new world. How did they form? Was there significant influence? The changes in minerals were playing. And it was parallel in the material science world. So the material scientists had long used electron microscopy, but not on this scale. They looked at line defects and faults, things of that sort, but they were not able to do this sort of imaging. Now they do, and I showed you a picture of zeolite. Well, all the big petroleum companies have electron microscopes. All the chip makers have microscopes. They're used widely. A lot of geology departments have them, but far more material science departments, physics departments. But no, good guess. Nice thing about a university is though you can just follow whatever as long as you get tenure and funding. And then you're free to do what you want.
All right, we have a question up here from Larry. We had one earlier. Yeah. For the people online.
Very fun talk, Peter. Your very last slide, you showed one of your bonus slides, the serpentine with all the little loopy-loops and things that said is unusual. Macroscopically, does that material look different than sort of the regular fibrous serpentine, or did you target that because it looked different?
Larry, I didn't get the question completely. You're talking about the magnetic field lines?
No, I'm talking about the TEM patterns. Your very last slide where you had the crystal
Looking
teal.
at the
Okay.
apple?
Nuttiness you discussed.
Yeah.
I'm asking if that particular sample looks different at the macroscopic scale, considering how crazy it looks at the nanoscale.
No, you don't see any of these things in the hand specimen, or even with the hand lens or optical microscope. No. It's a good question. Same thing I told you about WAD. The hand specimen, it just looks like black grunge. But when you look at it with EM, you see crystals. Well, same thing with carbonaceous chondrite.
Got a question over here from Mike. If you want to turn that microphone on.
Hi, Peter. Maitri here. I had two questions regarding the pseudocarbines. Why did you choose gold instead of any other element to work with? And when you say clusters, how big are these clusters?
First was
Why
gold. What was the other one?
How big are the clusters?
Oh, how big are the clusters? Okay. So first question, why gold? I think I told you, I'm going to get out of that beam. I told you how we stumbled on it. Harry Kroto called me I should look at this paper. There was a report that there was a group that used gold foil to connect to the laser beam, and it was just for the conductivity. And so they reported something that didn't make sense to us, not to Harry. He asked me my opinion. He didn't tell me hers. It didn't make sense to me. We wrote a letter. So then it didn't appear in the original journal. It appeared in another. It surprised us. I mean, that it appeared. We wrote a letter saying this doesn't make sense, and that was ignored. Moral of that is, if you have an idea where you disagree with someone, it really isn't worth the time to write a letter because it's ignored. So we decided we would embark on our own, and we knew that that group had used gold, and we knew that we disagreed with their results. So then we decided, how can we rationalize their results? And so, in a sense, we're using their data, but we're reinterpreting it in a way that we think makes more sense. That was the first question.
How big are the clusters?
Oh, how big are the clusters? I'd like to tell you. We don't know. We calculate. So I have a colleague named Tara, maybe some of you know, he's a theoretical chemist, and he calculates all sorts of, I'm not sure, single atoms, small clusters, larger clusters. I wish we knew.
All right, Steve, you have a question?
Yeah, Peter, I was fascinated by that slide showing catching metamorphism in the act. And I was curious if you looked at crystals at different points along a time, temperature, pressure path to see if you can get any kind of kinetic progression in that process. In different samples.
So this is a carbon
Yeah,
series?
yeah.
So what were you asking about?
Just to see if you got a time dimension on that. If you
Oh, the
looked at
time
different
dimension.
samples at different positions along a time, temperature, pressure path.
There's no time dimension. We looked at, initially, we wanted to look, as I said, we're looking for Precambrian life, and I thought we might see sort of fossils in the carbon. So we looked at kerogens. We looked at a lot of kerogens, lots of pretty pictures. They didn't show anything about life. They were very pretty. Then we looked at higher temperature to see what sort of organization there was, and that was the phyllite. And then I don't remember the third one, but the fourth, we looked at a high temperature hydrocarbon, and we saw increasing prophetization, but they're not a smooth sequence in terms of time. Again, we thought we could tell something about temperature and time from doing these things. It's another, I have a whole bucket full of great ideas that didn't pay off. That's part of it too.
That's great, thanks.
Rhonda has a question.
That was a perfect segue for the question I wanted to ask, Peter, which you must have a whole for things. You showed us ones where they were successful and important big picture questions. What are the ones where either the instrument or the samples didn't quite cooperate and those questions are still hanging at you?
Tom, I need your help again.
Yeah, you had all these great results. What are some of the things that didn't work?
Oh,
That you really wish would have worked, or you feel it was close. It was
things that didn't work. Is that what you're asking me?
things you think if the sample was a little better or the microscope was a little better would have. that you
Well,
still
maybe,
wanna-
maybe things that didn't work that might work now or in the future with a better
Well,
instrument.
let me
perhaps.
tell you about my first idea that I thought would be great. It was the early days with electron microscopy. The physicists were showing these homologous phases of titanium oxide. What that means, it's the ratio, the normal ratio of titanium to oxygen is 1 to 2, but they were finding some that were 1 to 1.999, 1.937. The exact number, a series of them. So I thought it would be really interesting if we could find these in reduced rocks and tell something about the oxygen fusion. So I collected eclogites, which are rocks that form deep in the earth, from a lot of localities. This is my first TEM project. And I did a sabbatical at Oxford. They just were installing their microscope. It was before we had ours. And all those eclogites, great idea, didn't see anything. I'll tell you another great idea, didn't pan out. It's a good topic. We found, it's also interesting, I had a postdoc from China who was looking at synthetic fullerenes, and I had a postdoc from Russia who was looking at natural rocks, asked me if I would mind if he looks at one from Russia. I said no. He knew what the man from China, he'd seen some of those images, but at the time, Russia and China, he had synthetic images, one and the other had natural images of fullerenes. So we had these natural fullerenes. That was the first report of natural fullerenes. We sat on it for a long time because we worried about it. Was it correct? Eventually we did mass spectroscopy. We established it. That was C60. Turns out chemists, physicists show that you can form a fullerene is like a soccer ball. It's exactly like a soccer ball. Carbon at each of there's 60 corners if you look at a soccer ball. You can make a larger soccer ball. It's not effective for playing on the field because it's a little distorted. It gets towards a rugby ball maybe. But you can make C72, C84, quite a few. So again, I thought, wow, this is great. We'll find these in different geological environments and we'll have a sensitive indicator. Didn't find that either. So you want more ideas? Didn't a lot of didn't work, but some did. Fortunately, some did.
It's got an amazing memory too, to remember all these.
sorry, what
A great memory to remember all these details from
But
so long
they're,
ago.
they're burned into my. I
Okay,
thought they
okay.
were so great.
I think we're about out of time. It's past 4:30 now. If let's thank our speaker again. This is a great talk. And if you'd like to say hi or come down and talk to him, he's here. For a few
Oh,
minutes.
don't go away. If you're enrolled in this class,